going to go ahead and open up today's session. So hello, everyone. Happy Tuesday. And I'm so excited to open up the session for today, the first Innovate of fall 2023. And today is a special day because we not only have a past student council member, but a very, very active member of the physics community. And I've been dying to hear about her research. So just a reminder, this is the Innovate seminar series, and it is the collaboration with the Kavli Institute for Theoretical Physics at the University of Santa Barbara. I am going to serve as also the Q&A moderator today, so I will be asking our speaker the questions verbally so that she can focus on coming up with the answer. And today, as our introducer, we have past president, Dr. Professor Stefan Alexander. And at this time, I'm going to turn it over to him to introduce our speaker.
Thank you so much, our esteemed student council leader, Ilan. And it's a real, I guess, a little bit of a dream come true almost, because a couple of years ago, right in the middle of the pandemic, when Lisa, Stuart, and I, and with the other NSBP leadership, decided to form this platform of the Innovate Seminar Series, NSBP Innovate Seminar Series. Whoever thought that it would come to, it's existed now for a few years now, and running strong. And so it's just a real honor to introduce one of our shining stars from Brown University. Farrah came to us as a PhD student in the year 2018. She had many great options for graduate programs that some, I guess, were even higher ranked than Brown. But I think, the fact that me and Professor Jim Gates were at Brown added a little bit of flavor to her decision. I would hope so. But things got even better, because not only did she transpire to be a stellar student and researcher at Brown University, winning international awards and all that good stuff, really setting the tone for what was to come at Brown University, where Farrah will be the first Black woman to get a PhD from Brown University, but also really led with her excellence to bring in, now we have 9 graduate students at Brown University, all thanks to her leadership and her exemplary excellence. I don't know if that sentence is correct, but anyway, you get my point. But let me just say a few quick things about Farrah. So she hails from Jamaica, and she came from Columbia University, and right when I became president of the National Society of Black Physicists, and the leadership at NSBP, we said we wanted to expand our student council. Farrah became the student council leader, and I think it's really clear, due to her leadership and her involvement and her just all of the hard work that she's put in. Farrah, I hope you can really smile and see all the wonderful things that's come to pass, and the legacy that you as a student leader are going to leave behind, because you're going to be graduating soon with your PhD this year. And so on that note, I guess, the bio is available, but I'm not one for reading bio. What am I missing from your bio here that's not covered? Let's see. I think also, you're involved in the arts in some ways, and maybe you can talk about that. Right? What type of what in the arts are you interested in? I think dancing, is it?
Yes, not recently, but
right. So on that note, again, we at NSBP are at loss for words. We're so fortunate to have this shining star, and on that note, I give you off to Farrah Simpson.
Hi, everyone. Thank you for the kind introduction. So I'm very excited to be here today to present my work on my thesis project on the search for the vector-like quark, the X5-3 at the Large Hadron Collider. As mentioned, I'm a physics PhD candidate at Brown University, and I'm also the immediate past student representative on the National Society of Black Physicists. And it was actually during my time on the board that this series came into being. So I'm very excited to be a speaker here today, and also just to see the series become what it is today, as a very important platform for NSBP members to share their research. So I first just want to thank NSBP and KICP for continuing to create this space for NSBP members. I spent the past year at Fermilab learning about all the experiments there, and I really have a deep appreciation for high energy experiment. And also I learned so much about the history of particle physics there. And so I just want to motivate or talk today by first speaking about why we performed these searches at the Large Hadron Collider in the first place. So the standard model of particle physics describes everything that we know about particle physics today. It's the best theory to describe these basic building blocks of the universe. It includes the quarks. We know the up and the down quarks make up the protons and neutrons, and the leptons and neutrinos. We're probably most familiar with the electron. And then we have our fundamental forces that are mediated by bosons. Electromagnetism is mediated by the photon. The strong force is mediated by gluons, and the weak force is mediated by the W and Z bosons. The Higgs mechanism describes the spontaneous breaking of symmetries in the gauge group of the combined electromagnetic and weak interactions. And it describes how the W and Z obtain their mass while the photon becomes massless, and explain how particles acquire their mass. Of course, this requires the existence of the Higgs boson that is in the center here. In order to validate the theories of the standard model, we search for particles at colliders. The W and Z bosons were discovered at the superproton synchrotron at CERN, and then further studied in more detail at the Large Electron-Positron Collider and Slack Linear Collider. The top quark was discovered at the Tevatron at Fermilab. And of course, there was the infamous discovery of the Higgs boson in 2012 at the Large Hadron Collider by the CMS and ATLAS experiments. Of course, the story is not complete. We don't know everything about particle physics and everything about the universe. There's still a lot of unanswered questions in the standard model, including charge parity violation due to the large difference between the amount of matter and antimatter in the universe, the origin of dark matter. The standard model does not explain gravity or include gravity, and the hierarchy problem. The hierarchy problem arises due to the quadratic divergences in the quantum loop corrections when the Higgs mass is renormalized. And so there are many beyond standard model physics theories that try to address these discrepancies. In a lot of these theories, new particles are predicted, such as vector-like quarks. Vector-like quarks transform like vectors under the standard model gauge group, hence their name vector-like. Their left-handed and right-handed components transform identically under the standard model electroweak gauge group. They predominantly mix with third-generation quarks. So in supersymmetric theories, bosonic partners of the top quark are predicted, while in many beyond standard model theories like composite Higgs and little Higgs theories, fermionic partners of the top quark are predicted. The X5-third is the heavy fermionic partner of the top quark with exotic charge 5-third. And so the existence of the vector-like quarks would cancel leading quantum loop corrections in the observed mass from the top quarks, and this would stabilize it. So how do we perform searches for these new particles that are predicted in these beyond standard model physics theories? At the Large Hadron Collider, protons are collided together, and their constituents or partons will interact. The detectors at the Large Hadron Collider can then reconstruct the events at the collider. So I'm a part of the CMS collaboration, and so we collect data specifically from the CMS detector. At the CMS detector, there are many layers, there are many subdetector layers that tell us information about the particle decays, including the momentum or energy, charge, and missing transverse energy. So in the inner layer, we have the silicon tracker. And in this layer, tracks of charged particles are left since they interact with the silicon. The next layers are the calorimeters. And the calorimeter measures energy deposited by electrons and photons in the electromagnetic calorimeter and by hadrons in the hadron calorimeter. The next layer is made up of superconducting solenoid magnets, which bend charged particles so that we can determine their charge and their momenta. And then we have a gas ionization detector that detects our muons. Then from all the information in these subdetector layers, we reconstruct particles using the particle flow algorithm in order to identify our muon or electron or charged hadron, neutral hadron, photon, and the missing transverse energy or missing transverse momentum that comes from the neutrinos since they do not interact with the parts of the detector. So the event that we are searching for here is the pair production of the X5-3. So an X5-3 and its antiparticle. And the dominant mechanism for X5-3 production is by quantum chromodynamic processes. And the vector-like quarks predominantly mix with third-generation quarks. So X5-3 is assumed to predominantly decay to a top quark and a W boson. The top quark can decay to a W boson or a B quark, and the W bosons can either decay to hadrons or leptons. And so we can look into many final states. We're interested in the single lepton final state so that we can maximize our sensitivity to our event here. And that means that the W's will decay to hadronically except one, which will decay to a lepton and neutrino. In order to maximize the sensitivity to the signal in our analysis, we take several steps. So first, we have to simulate the Monte Carlo process for the signal event. Then we perform an event pre-selection. We will calculate the expected cross-section limits, then optimize to obtain our results that are the observed signal cross-section limits after optimization is complete. There's no data in these sets until the results section when we have finished optimizing our analysis strategy. So first, for the Monte Carlo simulation of the signal event, we use models created by theories that provide a mathematical description of vector-like quarks. We simulate the signal event and the decays using a mass range for the X5-3 between 700 GeV and 1600 GeV with 100 GeV increments. And so on the right-hand side, you can see all our signal Monte Carlo samples, as well as their cross-sections. The cross-sections are proportional to the rate of the number of events. It's equal to the rate of the number of events is equal to the luminosity times the cross-section. And so we can just multiply the luminosity, which here for Run 2 2017 is 41.5 inverse femtobarns, by the cross-sections, which are listed here in femtobarns. There are many background processes at the collider that produce the same single lepton final state that we have to consider. So these can be categorized into top, which includes our single top events and our TT bar events, EWK processes that includes our W plus jets or Z plus jets and our di boson events, and the QCD multi-jet processes. So here are our background Monte Carlo samples for this analysis and their cross-section in picobarns. If you notice, the cross-section of the background samples are much larger than the cross-sections of the signal. So for every signal event, we will have many background events. And so that just shows how important it is in our analysis strategy in order to reduce the background contribution and maximize the sensitivity to our signal, which is what we do in the following steps. So from the particle flow algorithm, we combine the information from the subdetectors in order to reconstruct our particles and our particle jets. And we identify these jets using tagging algorithms, which I'll talk about in the next slide. But to perform our pre-selection, first we require one lepton, since we're looking at the single lepton's final state. There's a significant amount of jet activity in the signal topology, so we require at least 3 jets, with their transverse momenta being greater than 30 GeV. We also require that the scalar sum of the PT of all jets be greater than or equal to 500 GeV. Then we make selections on the eta value, or the pseudo-rapidity, which is a spatial coordinate describing the angle between the particle relative to the beam axis. So we want to focus on events close to the beam axis, so we require that the eta value of the jet be less than 2.4, and also make requirements on the lepton eta values. We expect neutrinos in our final state, and we also want to reduce the multi-jet background, so we make a selection on the missing transverse momentum. We require that it's greater than 80 GeV, and we expect B jets in our final state as well from the top decay, so we require at least 1 B jet. To identify the hadronic top and W jets, we use the particle net algorithm, and this is based on a dynamic graph convolutional neural network. It combines edge convolution with dynamic graph convolutional neural networks in order to treat the jet as a particle cloud or an unordered set of particles instead of an ordered set. So this is a more natural representation for our jets. B tagging is performed using the beat jet algorithm in order to identify jets that originate from B quarks. And we also have to perform tagging efficiency studies in order to correctly identify the number of jets in the Monte Carlo simulations. So here I'm showing a result from our tagging efficiency studies for top tagging using the particle net tagging algorithm. So here you can see the efficiency versus the top jet PT. And if you notice, as the PT increases, then we have higher efficiency. So at 1600 GeV, for example, about 93% of the time we'd identify the top jet correctly. Once we've performed our pre-selection, then we can make some data Monte Carlo comparisons. The pre-selection is a loose selection, so at this stage, we don't expect to see the signal. We expect that the data will agree with the background. And so we compare the data and the Monte Carlo processes here. So you can see the data by these black dots and the Monte Carlo background processes, the top EWK and QCD background, with the top being the dominant process here, as well as our signal at 1200 GeV here. And so we analyze the distributions of the signal and the background for several variables. Here I'm showing the HT variable and the min MLB variable, where min MLB reconstructs the visible mass of the top quark in the detector. And we see here that there is reasonable agreement between the data and the background, as is shown in the lower panel here. And this, of course, is in our pre-selection region, and that is what's identified here. The last bin is an overflow bin, so that is why the distribution looks like that in the last bin. Once we perform our pre-selection, we categorize our events, and we've used 16 total categories here based on lepton flavor, the number of B tag jets, the number of boosted W tag jets, and the number of boosted top tag jets. And so here I'm also showing the analysis that we did of the background and signal process for the background and signal processes for the HT variable in only one category, which is highlighted in yellow here and shown here. And so we can see our top background and our other backgrounds, which are not as dominant, as well as our signal sample at 1200 GeV again. Once we've performed our discrimination and our categorization, we can then look at optimizing our results to maximize our sensitivity to the signal. And I'm going to describe here how optimization was previously done. So I optimized by minimizing the exclusion limit and maximizing the expected significance over combinations of cut selections. The exclusion limit is calculated using confidence levels method that sets an upper limit on the signal cross-section based on the numerical evaluation of the likelihood ratio test that tests the compatibility of the signal and background model with the data compared to the background only model. And so here we can maximize our sensitivity to the signal by minimizing our exclusion limit. So here we varied the lepton PT cuts. So we made the lepton PT greater than 60 GeV, 80 GeV, and 100 GeV. And the minimum exclusion limit here corresponds to the green curve, and that corresponds to maximum sensitivity to the signal. So we chose 100 GeV as our lepton PT cuts. We similarly did this over the other variables, the number of jets, the missing transverse momentum, the distance between the lepton and subleading jet, the leading jet PT and the subleading jet PT, to obtain the optimized cut selection highlighted in green here. We also maximized by maximizing our expected significance, where the significance of a result is calculated using a ratio of profile likelihoods, one in which the signal strength is set to 0, and one in which it's free to float. And so the maximum significance here would correspond to the red curve, or a cut of 1.0 for the distance between the lepton and the subleading jet. And so this highlighted green selection, as well as the selection listed here, is the selection that maximized our significance as well. So that was chosen to obtain some preliminary expected sensitivities to our signal. And here I'm showing expected sensitivities to the signal cross-section using that optimized selection that I showed before. So here the red line shows the theoretically predicted cross-section, and then the expected cross-section also has error bands. So this is the 1 sigma error band, and the yellow is the 2 sigma error band around the expected cross-section. And so we obtained an upper limit on the signal cross-section, or an expected limit of 1,283 GeV. And this is our most sensitive result to date. We can compare it with the 2016 single lepton result, which was found to be 1,210 GeV. And this is calculated at 95% confidence level as indicated here. So we expect that we can make this even more sensitive to our signal, this analysis more sensitive to our signal using better optimization techniques, which I'll talk more about in the conclusion. But first, I'd like to introduce a new decay channel of the X5 that we're performing our search in. And this is in an exotic decay chain where the X5 is allowed to now decay to beyond standard model particles. So since vector-like quarks are always accompanied by additional beyond standard model particles, the presence of new physics allows us to look into the possibility of the X5 decaying to a singly or doubly charged scalar or vector boson. So here S stands for scalar boson and V stands for vector boson. And so here are the 4 exotic decay channels that we can look at. And these are all assumed to have branching ratio equal to 1. So we can look specifically at one of these decay channels, and so we select the singly charged scalar boson. And here all the boson masses are free parameters. If we make our analysis even more specific, we can specify that the singly charged scalar boson is a charged Higgs, and we can use masses ranging from 200 GeV to 1000 GeV as long as they're kinematically allowed based on the mass of the X5 third. So the charged Higgs has 4 decay channels that we can consider, and they all have branching ratio equal to 1. So we select the channel where the charged Higgs decays to a top quark and a bottom quark. And so then the top quark can decay to a W boson and a B quark once again, and the W's can decay to hadrons or leptons. And so we can look into a very similar signal topology as our previous search, and use very similar analysis strategies. And so that is exactly what we're doing. And we've obtained some preliminary results where we look at the shapes of the signal or the distributions of the signal for certain variables, for many variables. And here I'm showing the jet multiplicity and the distributions of the signal in not just our new decay channel, but also the previous decay channel to compare them. And of course, we expect higher jet multiplicity or more jets in the new decay chain, which is exactly what we observe here. We also looked at the leading jet PT, and we would expect that as the X5 third decays to heavier particles, then the leading jet PT would be smaller, which is exactly what we observe here. Of course, we vary the charged Higgs mass, and so we can compare as we increase the charged Higgs mass, then the leading jet PT, of course, becomes smaller as is observed. Here is also our results for the HT distribution, which doesn't vary that much between our previous model and the new model. And so we will obtain expected sensitivities for this new decay chain in the same way that we did for the previous decay chain. We will also repeat the analysis using 2018 Run 2 data that's collected at an even higher luminosity, so 59.97 inverse femtobarns instead of our previous 41.5 inverse femtobarns, so that we can obtain even more sensitive results. And we'll further improve the sensitivity to the signal by optimizing using machine learning tools. So currently we're performing a multivariate data analysis using multivariate classifiers. And these use machine learning tools such as neural networks and boosted decision trees in order to optimize our techniques for the classification between the signal and the background. So I just want to thank you all for listening. Here are my references in case you would like to read further about anything I've talked about, and I'll take any questions that you have now.
Hey, virtual claps, virtual claps. Thank you so much, Farrah, soon to be Dr. Simpson, for this talk. Very, very interesting. And also a really interesting application of machine learning, which I'm taking a class on. So I definitely have questions there, but I want to first open up the floor to our attendees that are logged on webinar style. So you can paste your questions in the Q&A option or into the chat, and I will read them to our speaker. If you feel like it would be better for you to verbalize, Alina, would you be able to promote attendees if they would like to speak their questions? Oh, Alina might have stepped.
I can do that if people want to
okay.
raise their hand. I'll be happy to.
Thank you. Thank you so much, Lisa. Okay. Keela, oh my gosh, we went to undergrad together. Hello. Happy Tuesday. So Keela Davis has a question about slides 17 through 18. It says this might be what you're using machine learning for. Okay. When you're optimizing event selection, is there any correlation between those parameters? Would your sensitivity increase by accounting for those correlations?
Yes, so we, let me just read your question again. Yes, there is probably correlation between some of the parameters, and we don't necessarily use all the parameters because we can use our machine learning tools in order to see which parameters would optimize the classification between signal and background better, and then use those parameters. So we don't necessarily use all the parameters, and they're not necessarily correlated. So it just depends on after we have done our classification and seen which classifiers work better.
A comment, excellent presentation and well explained. It's clear you know your work extremely well.
Thank
Yes, she
you.
does. Yes, she does. I had a question about, I guess, the machine learning. So I'm basically where I'm at in machine learning is I just figured out how to use decision trees and how to optimize your attributes based on your information gain. So can you dive into a little bit of these other two bullet points that talk about like neural networks and boosted decision trees? Like how specifically for someone who's just starting out with machine learning, how would that like drastically improve your data?
So it would improve sensitivities to specifically the search for the X5 So if you notice, the optimization techniques that I used aren't necessarily extremely sensitive to or specific signal. And so that is the goal of using machine learning tools in order to make it even more sensitive to specifically an X5 instead of any other heavy particle that you would see at the collider. So there are many different methods that you can use and many different variables that you can use. And so the packages that we use allow us to look at which are going to make the classification between the signal and the background the best, because that is our overall goal. Because as I showed, there's a lot of background contribution. There are a lot of background events for every single signal event. So then it can look at which classifies the signal versus background the best. And that's really the advantage of using the machine learning tools.
That's actually so interesting. So how long would it take? Like, are you able to test each of the models, or you have not yet to test these yet?
We're currently testing them. Thankfully, there are a lot of packages that allow us to test them very quickly, so it doesn't take a very long time to test them.
So what's quickly?
It depends how many parameters you use and how many tests you want to run, but I would say relatively probably just a couple hours, depending. But we also try to use as many possible techniques as possible. So it might take longer than that, depending on what we decide to use.
All right. Well, I've talked up enough of the time, so we got two questions here. So the first one is both from Brown. So the first one is from Max Pizzell, and he wants to know about the impact of the X5 on the hierarchy problem.
Okay. So I touched on this a little bit, but vector-like quarks, I mentioned that their left-handed and right-handed components transform identically under the standard model gauge group. So the symmetry allows the mass to be included in Lagrangian and doesn't depend on the Higgs-Yukawa couplings. So the X5, it will stabilize the mass. So it'll make those corrections to the leading order quantum loop corrections in order to stabilize the Higgs mass. I hope that answers the question that you're asking. So it's a solution to the hierarchy problem, essentially, but that is how it would solve the hierarchy problem.
Tana, I think you should be able to speak.
Yeah, can you hear me?
Yes.
Yeah, so for the last one, what optimization techniques were you thinking of employing specifically?
Okay, so I'm trying not to be too specific in terms of like what we use, just because it's very particle physics and high energy physics based, but the package that we're using includes implementations of several different techniques, and so it evaluates those techniques to see which classifies the signal and background the best. So as I mentioned, you can use boosted decision trees. You can also use projective likelihood estimations, multidimensional likelihood estimations, so things like that, and neural networks, of course, in order to look at which will discriminate between the signal and the background the best.
Follow up, are these like, are they Python packages or are you developing anything from scratch?
So we use packages in Root, and Root is specifically used in high energy experiments. So it already has built-in packages that allow us to do this very easily.
Thank you, and great talk, by the way.
It's called TMVA if you want to look it up, but it's a root package.
I have a question. You want to guess who the I am is?
Yes.
Yeah, this is, okay. First of all, great talk. Very, very, yeah. And so my question, let's see, in terms of your knowledge of the theoretical motivation, aside from solving the higher problem, are there any other maybe connections to this X particle? I like to call it the Malcolm X particle. You know? Anyway, the X particle with, say, astrophysics, maybe, you know, there are these Higgs particle models or anything to do, maybe connected with dark matter, anything like on that side of things?
Not really. The vector-like quarks mostly come out of these beyond standard model theories that try to address the hierarchy problem. I don't think there's dark matter application to the X5-third.
Well, I think you answered my question. You said they're charged under the standard model, so I take back what I said. My bad.
Oh.
Any other questions from our attendees before I ask another question? Okay, well, I'm just curious, and feel free to add questions while I'm asking. I'm just curious because the D word was mentioned, dark matter, and I guess I'm wondering, when you test the theories that you say are like beyond the standard model, how far beyond? Like, how far removed is the connection? I'm assuming it's not all the same for every model, but how far removed is it in the sense of explaining the fundamental concepts of this particle?
I'm trying to make sure I understand your question properly. So beyond standard model physics theories come out of the unanswered questions within the standard model. So either we have observations that are not explained by the standard model, or there are discrepancies in the standard model. So for example, the standard model doesn't include gravity. We obviously know gravity exists. And so there are beyond standard model physics theories that try to explain those discrepancies to make the standard model more complete.
That was a perfect answer.
Incompleteness of the standard model that we're trying.
Right. So it's a combination of like observations and lacking like discrepancies in the model itself. So it is coming from both like an experimental and a theoretical computational place.
Right. So the theories predict the existence of these new particles, and we perform searches for these new particles. So the Higgs mechanism, of course, was nicely summarized what we already knew, and it wasn't confirmed until we performed searches and discovered the Higgs boson, because the Higgs mechanism requires the existence of the Higgs boson. So that's just an example of how the experiment relates to the theory.
Thank you for that answer. That was perfect. I think at this point we have time for one more burning unanswered question. If you have anything for our speaker, I'll give it some time for you to type or raise your hand.
Elon, can I ask a question? This is Steven.
Absolutely, President-elect. The floor is yours.
I might have missed it because I've been kind of doing work and paying attention with one eye. But Farrah, so what I've noticed is that this presentation you're giving is basically telling people where to look. Am I understanding that correctly?
Well, we have looked, and it kind of shows some preliminary results from that search.
So would you say that what you've seen corresponds to what you have predicted in your calculations? Would you say it falls in line or no?
So far, the analysis shows that our strategy is reasonable given that the data matches the Monte Carlo. However, we cannot obtain any results or observed signal cross-section limits without unblinding. So unblinding is including our data. So if you notice, I haven't included any data in this plot. And so once we unblind, we will include our data, and that is done at the final step once our optimization is finished. So we haven't completed optimizing our result to maximize the sensitivity to our signal event. So once we do that, then we can include our data and obtain some observed results.
Do you have a sense whether or not you will be successful with what you have, or is that analysis required to give you a yes or no that you have what you think you have?
We don't generally expect to see an excess, so we can claim discovery at 5 sigma. And below that, we can't claim discovery. Below 3 sigma is statistical fluctuation. So we don't expect that we will see anything. We don't expect a discovery, but what we can do is set an upper limit on the mass of the x5/3, which is what we're doing here. And so we can present the most sensitive results for the limit on the x5/3 cross-section, which tells us even more information.
Okay, thank you.
Alrighty, so with that, I would like to close our session for today. Thank you so much, Farrah. Appreciate you.
Thank you, everyone.
For our attendees, the session is now over. Stay tuned for our announcement of our next speaker, and thank you as always for logging on, for opening this YouTube video. However you're watching this, I appreciate you logging on, and the Student Council appreciate you as well. So everybody have a happy Tuesday, and I'm wishing you a productive rest of your week.